Calgary Framework 20 is a leading candidate for use in CO2 capture from humid flue gases and from humid natural gas. An important feature of CO2 water adsorption in CAF20 is the prevalence of strong thermodynamic non-idealities. In order to demonstrate this, I plot the experimental data of Rajendran and co-workers published in Chemical Archives 2024 as a function of the percentage relative humidity. The blue triangles are the component loadings for water, and the red circles are the component loadings for CO2. These experimental data are determined from breakthrough experiments. There are significant deviations of the experimental data for CO2 and water loadings from the IAST estimates that are indicated by the dashed lines. In order to quantify the mixture adsorption equilibrium, we need to adopt an appropriate model to describe the activity coefficients in the adsorbed phase. I use here the NRTN model for the activity coefficients. This plots the Gibbs excess free energy as a function of mole fraction in the adsorbed phase, and the red symbols are the experimental data points, and the continuous black line represents the NRTL model. A special feature of the experimental data is the existence of two different regimes. For percentage relative humidities lower than about 50%, the adsorbed phase is richer in CO2, i.e. poorer in water than the estimates of the IAST. On the other hand, for percentage relative humidities in excess of 60%, the adsorbed phase is poorer in CO2, i.e. richer in water than anticipated by the IAST. I plot here the activity coefficients in the adsorbed phase for CO2, red circles, and for water, blue triangles, as a function of mole fraction in the adsorbed phase. The RAST modeling for mixture adsorption equilibrium is described in detail in my previous publications in separation and purification technology. Watch also my presentations on thermodynamic non-idealities in CAF20 on my YouTube channel. The transient uptake within single crystals of CAF20 is described by a set of partial differential equations shown here, where Q sub I represents the molar loadings of component I. Component 1 is CO2, component 2 is water. N sub I represents the intra-crystalline diffusion fluxes, and in the Maxwell-Stefan diffusion formulation, the intra-crystalline fluxes are taken to be proportional to the gradients of the chemical potential gradients. The chemical potential gradients may be related to the gradients in the molar loadings of components 1 and 2 via a two-dimensional matrix of thermodynamic correction factors that may be determined from the expression to quantify mixture adsorption equilibrium. In our case, we use the NRTL RAST model to describe equilibrium between the bulk gas mixture and the external surface of the CAF2 crystallites. For the simulation results I will present in the subsequent slides, I use a crystallite radius of 2 millimeters. For background on the Maxwell-Stefan diffusion formulation, I invite you to read my papers published in Chemical Engineering Science 2019 and Chemical and Bioengineering 2024. This is an ACS publication. There are also numerous number of video presentations on the Maxwell-Stefan diffusion formulation, and I'll list some of the important ones here. These may be viewed on my YouTube channel. Let's proceed to look at the results for transient uptake within single crystals of CAF20. I show the simulation results for 3 different values of relative humidity: 25%, 50%, and 90%. The water uptake is indicated by the blue line, and the continuous red line indicates the CO2 uptake. The water uptake data is reported on the y-axis on the left-hand side. The right-hand side shows the CO2 uptake in the units of moles per kilogram. The dashed red line are for the IAST model for CO2 uptake, and the blue dashed lines are for the IAST model for water uptake. We note that the uptake of water in both the RAST and the IAST implementations shows a pronounced overshoot in the component loading of water. This overshoot signifies the manifestation of supra-equilibrium loadings within the crystallite and signifies the occurrence of uphill diffusion. This uphill diffusion is engendered by the off-diagonal elements of the matrix of thermodynamic correction factors. In several papers of mine and in several video presentations, I have demonstrated that if we take the matrix of thermodynamic correction factors to be the identity matrix and set the off-diagonal elements to 0, then the overshoots of water will disappear. But that discussion is well known. I proceed with showing you the results for 50% relative humidity and 90% relative humidity. These also show overshoots in the water uptake at a certain time interval. Eventually, the component loadings would equilibrate within the crystallite. It now remains for me to present you video animations for the uptake for 25% relative humidity and the RAST NRTL implementation of mixture adsorption equilibrium to help you visualize the maximum in the water uptake and occurrence of uphill diffusion. I will show you animations of the uptake of a mixture of CO2 and water inside CAF20 exposed to a bulk gas mixture at 25% relative humidity. The simulations are for the NRTL model for activity coefficients, and the uptake animations are plotted as a function of a dimensionless length along the crystal. R sub C equals 1 represents the external surface area of the crystal that is exposed to the bulk gas mixture, and the surface of the crystal is in equilibrium with the bulk gas mixture. At this position, corresponding to RC equals 0, this is the center of the crystallite. The y-axis represents the loadings of the components in units of moles per kilogram. This is a loading of 0, and this is a loading of 8 moles per kilogram. In the animations that you will see in a minute, the CO2 loadings are indicated in red, and the water loadings are indicated in blue. So here we go. Watch the development of the loadings that start from the right-hand side that is exposed to the bulk gas mixture. We note that the water enters the crystal far more quickly than CO2. This is due to the much higher diffusivity of water within CAF 20. And we note that the water loading shows a maximum in the lowering. As the profiles develop, I'll have you look at the loadings once again. Note that the water loadings show a pronounced maximum, and the maximum traverses from right to left. The compositions of the loadings of CO2 and water at the surface of the crystal are constant, and the system equilibrates to a situation in which the CO2 loading is significantly higher than the water loading throughout the crystal. However, during the initial stages of development of the loading profiles, the water loading exceeds that of CO2 and experiences uphill diffusion. That was it, folks.